Hello, ladies and gentlemen, and welcome back. Welcome back. We're looking at question 4 in this video. Question 4 from the 2011 Manitoba Math Contest. Question 4a says, let n be the product of the first 30 positive integers. Okay, so it's 30 factorial. In how many zeros does the base 10 representation of n end? Okay, that's an odd way to phrase that, but understand what this is. How many zeros are on the right? Okay, how long is the string of zeros on the right? Well, how do we make a zero up here? Okay, probably the first divisibility rule that anyone learns is how to tell whether or not something is a multiple of 10. Is something divisible by 10? And that's if there's a 0 at the end. If you got a 0, you're divisible by 10. No 0, not divisible by 10. Okay, so what does it mean to be divisible by 10? You need to have a factor of 2 and of 5. Okay, so there's actually a formula. I mean, it's not the nicest thing to work out, and it's not put in n and square it and minus double it and that sort of thing. But there is a general way to actually figure out these the number of zeros at the end of any n factorial. So maybe I'll talk a little bit about that. So n is just 30 factorial, but in general I'm going to talk about k factorial. So we get a 0 at the end for each factor of 10 in the number. Now that doesn't mean 10, 20, 30, so there's going to be 3 zeros. No, no, no. How do we make a 10? It's a 2 times a 5, and that's what we need to consider. Now, there in the first, so remember what factorial means, by the way. Just multiplying all the numbers up. So there are always more factors of 2 than factors of 5. This is sort of a general fact. You can look at it and say, yes, I can see why that's true. If you want to, write a couple sentences of explanation. But I think it's straightforward, and I'm going to leave it like that. So what really matters? The factors of 5. However many factors of 5 you have, there's going to be more than enough 2's around to pair up every 5 with a 2 and get a factor of 10. So my conclusion is number of zeros at the end equals a number of factors of 5. Okay. Well, how do we count the factors of 5? Very simply. The factors of 5 are going to come from the multiples of 5 in your product. And then you're going to get an extra factor every multiple of 25, an extra factor, so 3 factors of 5 every time you have a multiple of 125. Now, 125 isn't going to come into this 30 factorial case. But the number of factors of 5, there's going to be 1 for every factor of 5, or every multiple of 5 between 1 and k. And there's a quick way to express that as the floor of k over 5. So this is the greatest integer less than or equal to k over 5. Then there's going to be an extra factor every time there's a multiple of 25, because 25 has 2 5's in it. An extra factor every time there's a 125. An extra factor every time there's a 625, because this is k to the 4. Or sorry, 5 to the 4. And it just sort of keeps going on like this. Now for 30, we'll have 30 over 5, floor of that, plus 30 over 25, floor of that. There's going to be no 125s. So it's just going to be 6 plus the floor of 6 over 5, which is just 1. So 7 zeros. Okay. Now, they were careful in the question to say base 10 representation. If you shift to different bases, okay, so if you had base b, you would need to factor b into a whole bunch of prime factors, and you would sort of need to count how many of those factors are here. And one of these, the bigger one, let's say PM, is ultimately going to be one of the things that limits you. Also, if you have a really high exponent here, you can run out of factors of the smaller ones. But it's interesting to generalize this sort of formula to different bases. They didn't ask us that in this question, but there's your general answer, period. This sort of a question I've seen it on more than one contest in the past. So it's a nice little exercise to understand, where do zeros come from? Okay, the fives are the thing we really need to count. How do we count factors of 5 in this product? Interesting stuff. So that's 7 zeros there, and that is for A. For B, find a pair of positive integers, A and B, that satisfies A squared minus B squared is 2011, the year of the contest. Okay. So I immediately recognize the left-hand side here is difference of squares, and that has a nice way to factor it. So if I have A squared minus B squared is 2011, I can factor this side as A plus B times A minus B. Now, if A and B are positive integers, these are going to have to be positive integers. Well, integers. But if one of them is positive, A plus B has to be positive, so A minus B will have to be positive because the product is positive. But I don't think you really need to explain that. I'll just say that, these are integers as well. And they're integer factors of 2011. Okay, so could I find a pair of factors of 2011 so that if I let A plus B be one of them and A minus B be another one of them, I can solve for A and B? Well, you betcha. If I let A plus B be something and A minus B be something, line them up, add these two together, I'll get 2A is the sum of the two factors. So that'll be something plus something, and A will be the something plus something all over 2. And I can line them up another way, and yet 2b is the difference in the factors. So something minus something, and that would tell me b is something minus something all over 2. Now we would need the difference and the sum of these factors to be even. So we need either 2 odd numbers or 2 even numbers. Now we're not going to get 2 even numbers because 2011 itself is odd. In fact, any pair of factors here will have to be odd. So there's probably lots of a's and b's that will work. I think the easiest one to deal with is just 2011 and 1. In fact, I don't even know, is 2011 prime? No idea. Doesn't matter. We can get this answer here. So 2012 over 2. So A could be 1006. And B would be 2011 minus 1 over 2. So that's 2010 over 2. So 1005. So that's not really a therefore statement, but A equals 1006, B equals 1005 will suffice. Okay. And we only needed to find a positive pair. We didn't need to count all of them, probably because you would need to show 2011 as prime. But remember, calculators aren't permitted, so you'd have a heck of a time trying to actually remember whether or not 2011 is prime. Sometimes it's a good thing, and this doesn't happen a whole lot, but if you'll notice, a lot of math contests like to use the current year somewhere in some question. So sometimes it's it's the 2011 paper. Go into the contest maybe knowing how to prime factorize 2011. Is it prime? Is it a nice sum of 2 squares in multiple ways? These sorts of things come up. I remember, I think it was an Asian Pacific Math Olympiad in something like, I think it was 2003. And one of the questions involved chopping a triangle into 2003 smaller, similar triangles. I think all of them had to be congruent, and then they all had to be similar to the big one. And there was a really quick way to do it if you realized that 2003, and maybe it wasn't 2003, but whatever year number it was the sum of these two squares. And then the whole thing dropped out really, really quickly, and it was quite interesting. So sometimes going into the contest knowing things about the current year number will help you out. Not always, but sometimes. So it's something to sort of have in mind. Okay, so that wraps up question number 4. In the next video, we're going to take a look at our next question, question 5. I hope to see you guys for that one in the next video.